In this video, we're going to talk about gases and how we think about the number of molecules or atoms in a gas using important gas-related variables. And gases are obviously all around us. One thing you may not have considered before is that a lot of the measurable variables that we think about with gases, things like pressure and volume, are related to the number of particles in the gas, the number of moles of gas present. And because of this connection to number of particles, I wanted to include this video in this module, since for gases, it's actually relatively easy to use measurements like pressure and volume to count molecules. And in fact, the counting of molecules using gases was part of what led Avogadro to the perspective in the 19th century, way before, might have even been the 18th century now that I think about it, way before a lot of other people led him to this molecular perspective on matter, that matter is made of very, very tiny particles, and gases are no exception. So in this video, we're going to take a look at gases in general first, talking about things like pressure and volume, general variables that we're concerned with gases and how we think about them as the most dispersed state of matter. And then we'll talk about the ideal gas law with a particular emphasis on the insight it gives us into counting molecules in a gas using variables like pressure, volume, and temperature. As we've seen before, gases are the most dispersed phase of matter. Particles within a gas are very far apart from one another, and they're in constant motion. And so the image we have in our head for a gas is a bunch of very tiny particles with a lot of empty space between them, moving relatively rapidly. So they're colliding with the walls of their container, they're colliding with each other on a regular basis, and they display a distribution of speeds. Generally speaking, for a gas that's at equilibrium, we think of the particles as uniformly distributed over space, such that the gas expands to fill the volume of its container. This means that the volume of the container is the volume of the gas. In a balloon, for example, the gas takes up the full volume of space inside the balloon. There is no vacuum in there. The gas is everywhere all at once. Particles that strike the walls of the container push on the container in the course of doing that, right, and bounce off, and they exert a force in the process. That force is related to a phenomenon that we experience as pressure, which is the force divided by the area over which that force acts, the surface area on the inside of the container. And that force per unit area is what we call pressure. Now, the mental image you want to have in your head here is the gas particles here in red are striking the wall of the container. As they do, they exert a force, and that force is divided by the area to find the pressure. And so units of pressure can be things like units of force and length squared, units like newtons per meter squared, that's a Pascal, or pounds per inch squared, etc. They can also be related to the atmospheric pressure. There's a unit that's called the atmosphere that's just equal to the pressure exerted by the Earth's atmosphere at sea level. We can also measure pressure using the height of a column of fluid. I won't get into this in any detail here, but you'll see units like millimeters of mercury, inches of water, feet of water, where the pressure exerted at the bottom of that column of fluid can be compared to the pressure of a gas, and other units like this. So one thing we can note about pressure is that if we have more particles in the system, all other things being equal, the force those particles exert on the walls will be greater. So we have reason to believe that pressure is directly related, not necessarily linearly related, but at least directly related. As one goes up, the other goes up. Pressure is directly related to the number of moles of gas inside a system, and we'll see very, very shortly that this is the case. There's a particular model we use to think about gases on the submicroscopic scale, and it's called the ideal gas model. When I teach about gases and the ideal gas law, I emphasize that it's actually this submicroscopic picture that is the most important thing to understand about gases, since as you advance in your study of chemistry, what you'll find again and again is that our models for understanding chemical reactivity and even solutions and a number of other things are built on this simple but important model of gas behavior. The model assumes that the particles don't interact with each other, And so, in essence, every particle has access to the entire container and is not influenced by any other particle. It assumes that the particles take up no volume, which is a bit trippy to think about, but reasonable given the large amounts of empty space between the particles. And that collisions conserve kinetic energy, meaning no energy is internalized when gas particles collide with each other. All of the energy of an ideal gas is simply in the motions of the particles. And those motions are not all uniform. Different particles are moving at different speeds, and what we see is actually a distribution of speeds. Some particles are moving faster, some are moving slower, most are somewhere in the middle. At the bottom of this slide, I link to a simulation that'll give you a great feel for the ideal gas model, and it will actually show you how the ideal gas equation of state, or the ideal gas law, arises naturally from the assumptions of the ideal gas model. This simulation, which has no knowledge of the ideal gas law, nonetheless spontaneously spits it out at equilibrium as the particles collide with each other and come to equilibrium. It's pretty neat, and it will give you a great feel for the ideal gas model and the ideal gas law. From the ideal gas model, we get an important equation that relates the most important variables of relevance to gases: pressure, volume, temperature, and number of moles. And for our purposes in this module and in this unit where we're talking about counting molecules and number of particles and number of moles, it's really the number of moles here that's the most important to us. This equation shows us that by measuring pressure, volume, and temperature, we can infer the number of moles of gas in an ideal gas system. So in the equation, we have pressure times volume on the left, and on the right, we have the temperature in Kelvin. This needs to be an absolute temperature. We have a constant of proportionality that's called the gas constant. Here it's given the symbol R, and we have number of moles. And if we're interested in counting gas particles, this is often what we're interested in solving for. That's kind of why I set it off in orange. The gas constant has a value of 0.08206 liter atmospheres per Kelvin per mole. So notice, atmospheres, that's a unit of pressure. Liters, that's a unit of volume. Kelvin is our temperature unit, and then per mole, and that's our unit of amount of substance. And so we can use this value of R to calculate, for example, number of moles if we know the other three variables that we've indicated here. If P, V, and T are known, the amount of gas can be calculated using the ideal gas law. And here's a rearranged version where we see that the number of moles is equal to the pressure times the volume divided by the temperature and divided by the gas constant. So let's work a quick example problem to see how this works in practice. Say we wanted to know the number of moles of oxygen gas, O2 gas, in a cylinder with a volume of 2 liters at a temperature of 293 Kelvin, this is approximately room temperature, and 1 atmosphere of pressure. Well, we start with this rearranged version of the ideal gas law, right? N is what we want to calculate, and actually even before doing that, it's good to visualize this, right? We simply have the oxygen gas in a box. That box has a volume of 2 liters, and we've measured the pressure, and the pressure is 1 atmosphere. And from the ideal gas law, we know that N is equal to P times V. Here I've done that, 1 atmosphere times 2 liters, divided by the gas constant times the temperature. And it's good to notice here that there's unit cancellation that goes on that will bring moles into the numerator and leave moles as the only remaining unit. So for example, atmospheres cancel out. The atmospheres in pressure and the atmospheres in R divide out. The liters and the volume and the liters and the gas constant divide out. And then the temperature divides out in the gas constant and the temperature here, leaving moles as the only remaining unit. And that's going to flip to the numerator as it's in the denominator of this calculation, so it'll flip to the numerator. And when all is said and done, we arrive at 0.0832, or about 83.2 millimoles of oxygen gas in this system. So we can see here that if we know the volume, we know the temperature, and we know the pressure of a gas, we can infer the number of moles of gas. On the next slide, what we'll see is that we can use the ideal gas law with proportional reasoning to take advantage of the idea that number of moles is actually linearly related to pressure and to volume. To understand how we can connect proportional reasoning with the ideal gas law, we need to start with this idea of holding some of the variables constant. So first I want you to imagine that we're dealing with a system that's at constant temperature and pressure. And a classic example of that is actually a balloon, where the flexible walls keep the pressure at 1 atmosphere, but the volume can vary as the balloon expands or contracts. In this situation, volume is proportional to number of moles, and this can be derived from the ideal gas law. If T is a constant and P is a constant, then V is equal to a constant times the number of moles, right? And so as we add moles, the volume goes up. As we remove moles of gas, the volume goes down. And this is very easy and intuitive to see with a balloon, right? The general idea here is something like this, where say we started with a container A with a volume V and N moles of gas. We had a container B with double the volume. If the pressure and temperature are constant, this implies that double the number of moles of gas are present in that container with double the volume. And on a graph, this means that volume and number of moles are related linearly, right? These 2 points A and B are 2 points on this line, and the linear relationship follows from the linear relationship built into the ideal gas law between volume here and number of moles here. Similarly, if we hold the volume constant and the temperature constant, pressure is proportional to number of moles, and this is something like a bicycle tire, right, where the volume is pretty much fixed. There's a little bit of flexibility there, but not a ton. When you get to high pressures, the volume is pretty much fixed, and as we add gas into the tire, the pressure goes up. And again here, we're dealing with a linear situation. So if I start with a container A that has a pressure P and N number of moles of gas in it, if there's a container B at the same volume with double the pressure and the same temperature, this implies double the number of gas particles, or double the number of moles, right? And on a graph, pressure and number of moles are related linearly, and these two containers A and B are like 2 points on this line, derived from the linear relationship between pressure over here in the ideal gas law and number of moles over here. Another way we can say all this is that, well, first of all, these equations here are another way of expressing this idea of a linear relationship between V and N or P and N. The slope here of these lines is a constant, and the slope is also V, the volume, divided by N, the number of moles. So V over N at any point on this line is equal to V over N at any other point. P over N on this line is equal to P over N at any other point, right? This is just an expression of linearity. And what this means in terms of knowns and unknowns is if we know the pressure at one point and the number of moles at one point, and we know the, say, a different amount of moles in a related system, we can find the pressure corresponding to that different amount of moles. If we know the volume at one point and the number of moles that it corresponds to, we know this ratio of V1 over N1, and so we can find the volume V2 for a different number of moles, N2. We could find the number of moles corresponding to a different given volume as well. I haven't shown that on the slide, but of course we could switch this known and unknown, and the basic idea would be exactly the same. So let's work an example problem to see how this pans out in practice. We're told that a sample of this number of moles of H2 has a pressure of 1.86 atmospheres, and we want to know at what number of moles would this gas display a pressure of 3.12 atmospheres with no change in temperature or volume, meaning T and V are held constant. So we're dealing with this idea here, and we know the ratio of pressure to number of moles. It's given by what we underlined in blue here. Pressure is proportional to the number of moles, meaning this ratio is constant for this gas. 1.86 atmospheres divided by 0.352 moles is a constant number of atmospheres per mole that holds for this gas regardless of the number of moles present. What we can do now, recognizing that this ratio remains constant, is set up an equality of two P over N expressions. The first given to us in the problem, 1.86 divided by 0.352, and the second coming from the given desired pressure of 3.12 atmospheres and our unknown number of moles, N2. And now all we have to do is solve for N2, for example, by cross-multiplying. That will lead us to N2 is equal to this ratio times 3.12 atmospheres. And when we calculate all this out, the atmospheres divide out, of course, and we're left with moles. And this comes out to 0.590 moles of H2. And notice, this is quite a bit higher than the 0.352 that we started with or had at 0.1. This makes sense. To achieve the higher desired pressure, we need a bigger number of moles here than the number of moles corresponding to the lower pressure of 1.86 atmospheres. This is actually where I want to leave gases. We've really just barely scratched the surface of what's going on with gases, and you'll get into gases on a much deeper level in your introductory chemistry course. Some lingering questions I'll leave you with. What other relations between gas variables can we infer from the ideal gas law? Here we focused on number of moles in all the relevant relations, but there are other relationships, for example, between pressure and volume when the number of moles is held constant, that are also important to explore. What about a mixture of two or more gases? How does the ideal gas law apply there? How do we use the ideal gas law to plan and carry out reactions involving gases? This is related to the topic of stoichiometry that you'll study in your introductory chemistry course. And then what happens when the ideal gas model breaks down? What happens when we get into the real world where gases don't exactly behave ideally under all circumstances? How do we model real gases? What are the conditions under which we might expect a gas to behave in a, say, less ideal way? Or does the ideal gas law always apply without exception? These are questions that you'll answer or explore in your future chemistry studies.